Hey, Rachel. Thank you for inviting me.
Yes, of course. Jeff, are we live or no?
Yes, you're good to go.
Okay. All right. So good morning, everyone. Sorry about the late start, but welcome to the remote experience for young engineers and scientists program known as REYES. My name is Rachel White, and I'm a member of the REYES planning team. I will serve as your host for today's lecture, How is it to live with a star, featuring Milo Buitrago Casas. Today's discussion offers us insight into the newest ways we currently have to explore solar dynamics, recent findings, and challenges to come in the next few years. Throughout this webcast, you may submit questions through the Q&A box on your Zoom screen. Following this lecture, we will answer as many of your questions as time allows, and it is my pleasure to introduce our guest speaker. Milo is a postdoctoral associate with the Space Sciences Laboratory at the University of California, Berkeley. He focuses on astrophysics and space science. In particular, he participated in NASA programs that seek to implement new technologies for observing the sun with space instruments. He also has a permanent interest in broad access to high-quality education. He is a founding member of groups and collectives in the area of astronomy in Columbia and an active member of the education and public outreach team of the Solar Physics Division of the American Society of Astronomy and Science Clubs of Columbia. Please join me in welcoming our speaker to REYES.
Thank you, Rachel. So I'm gonna try to share screen here. Let me see if this works. Okay, can you guys see my screen?
Looks good to me.
Okay, sounds good. So thank you for the invite, and I'm so glad to be here with you all. Please submit your questions. I'm gonna try to keep my eyes on the chat to see like if some questions pops up. I'm gonna, before going into the topic of the talk, which is how to live with this star, I just want to mention a little bit about me. So I'm originally from Colombia. Colombia is this part of the planet in South America, same continent as here, the whole America. And I'm a Latino, meaning I'm 50%, my foundations, my origins are 50% indigenous and 50% Europeans. It happened that, yes, I was born in this part of the planet. I'm a first generation. Both my parents completed only second, third grade, something like that. I'm the first one to finish high school, going to college, doing a master, going outside my country, coming to the US, finishing a PhD, all of that. So if there are first generations in this meeting, well, we share something in common. Let's see. Oh, before going also forward, I'm also very proud to say all my education has been fully funded by citizens of both Colombian and the US. I studied all my life in public institutions since kindergarten. I studied I was born in Bogota, the capital of Colombia, and I studied in a public school called Sorrento. It's in the main city. And then I went to do my undergrad in physics and my master in astronomy in la Universidad Nacional de Colombia, also located in Bogota, and then came here to the US, where I did my PhD in the largest, most prestigious public university in Berkeley. So that's also like to say a few things about public education. It's good. Okay, let's now move into the topic of today's talk, which is how to live with a star. And when I say live with a star, I don't mean living with any of these stars, but most fabulous star which is near us, and is this sphere of hot plasma that is basically the source of life in our planet. So the sun, it's how is to live very close to this star. And the reason is, yes, we all know is the main source of all kind of life and all kind of energy that we have here in our planet. Several of us dedicate our life to study our star, our sun, and people, scientists who dedicate their lives to understand the physics and the science beneath all the different phenomena and processes at the sun. We are called solar physicists or solar astrophysicists or heliophysicists. So all of that, all of us, we share something in common, which is, well, why it motivates us to study the sun? Well, it in part is because it is our fuel. If you say, okay, but I have my car and it works with gasoline, it turns out that that gasoline comes from petroleum, and that petroleum is not other thing but solar energy that came to Earth and did the photosynthesis on several trees, and then they died, and then after many years later, it turned into the petroleum and into the oil that moves your car today. So in one sense or the other, the sun is our fuel. We studied also the sun because it is a source of inspiration, and I bet like this is a picture taken here from the Bay Area. I'm located in California, at the other side of San Francisco, and you can see here, from here you can see the Golden Gate, and I bet you guys have also taken beautiful images of the sun at that sunset or at the sunrise. And okay, I can try to speak louder. Okay. Yeah, so I bet you guys can have taken pictures like this one. So it is not only a source of questions in science, but it is also a source of inspiration for many of us. Why to study the sun? Well, because it is very close to us. And at this moment, I have to say that our astrophysicists, our fellow astrophysicists are some sort of jealous at us, solar physicists, because if you go to an usual night astronomical observatory, you'll see a dome, a beautiful dome like this one. This is also very close to the Bay Area. This is in the mountains in Oakland, in Chabot. You can see for night astronomers, the objects of study, they are the stars over here, and they can choose like any star. Some of you guys probably identify that this is the Orion constellation, and what they do usually is just to point the best and largest telescopes that they have onto one of these objects. And unfortunately, like most of these objects into the sky, they look like a really tiny point, and they have done amazing things, but I bet they wish they could take as beautiful images of their astronomical objects as we can do with the sun. The fact that the sun is very close to us, it allows us to take pictures like this one. This is what I'm showing you here is the image with the highest resolution in extreme ultraviolet that we have taken of the sun so far. This was taken in particular with a sounding rocket payload called HiZ, and you can see the whole sun in here, and you see some kind of hair structures, hair-like structures over here, that if you zoom in, which is the image on the right, well, you see like way more structures, and then you can start seeing like, yes, hairstyle filaments in here that indeed have like, they have a lot of physics in it that we could go deeper if we wanted. Anyways, how the sun looks right now. This is how you would see the sun right now if you go out, if it was not cloudy like it is today here in the Bay Area, and with some of the special solar glasses, not the sunglasses that you use to go to the beach, but instead like those that you use for to look at the sun during solar eclipses. If you take one of those glasses and look at the sun, you'll probably see something like this. Or if you go to an astronomical observatory or a planetarium and ask somebody to put a solar filter on a telescope and point to the sun, right now, this is what we just see, which is basically, yes, a sphere of gas with some dark spots over here that we call sunspots. So yes, this is what we can see right now. Some people make jokes about us solar physicists that we can only study the sun during the day, and that's not true. We can even see the sun at night, and the reason is we have a spacecraft orbiting Earth and pointing constantly to the sun. This is an example. This is the Solar Dynamic Observatory that was launched in February 2010. And that has been constantly looking at the sun since then. The image that I showed before, it is an image taken with this spacecraft, but this spacecraft not only has instruments to observe the sun in what we call the visible light, but it also has instruments at these 4 telescopes over here on top of the golden ones that can observe the sun in extreme ultraviolet. And this is how the sun looks right now in extreme ultraviolet. So these 2 images are the same sun almost at the same time, but showing different structures. The key factor here is that this second image in ultraviolet, it is showing us structures of the sun that are higher in its atmosphere, structures on the sun that are at a higher temperature, are hotter than the structures that we can see with our own eyes over here. So you see some very interesting features in this image over here. Like you see there is more structure close to the belly of the sun, and it is kind of bold at the poles of the sun. Like here and here, there are not so many structures. If you take the 13 years of solar observations with the Solar Dynamic Observatory in extreme ultraviolet and kind of overlap all those images one on top of the other, you see this composition over here that I like very much, which shows you that in fact, close to the belly of the sun is way more active. It shows more activity, more structure. Except like at the very, very center here that we'll see a little bit of why. This is how the sun looks also right now in different wavelengths. So you see the sun, well, this is the focus, but this is visible light. And then you have many images here in false color, meaning scientists put some green or cyan or yellow or gold or golden here in terms of kind of make the image more easy to understand. But our eyes, the human eyes, cannot see these wavelengths and this kind of light. But you see all different structures. This is a little bit of very hot plasma almost going into the soft X-rays. And on the bottom here, you see magnetic field on the very left. This is visible light, and this is something that we call Dopplerograms that are very interested to look at, to understand how the sun is inside, beneath the layer of the atmosphere that we can see with our eyes. We can make reconstructions on how the sun has looked in the last, say, 24 hours or a few days. And you see that using observations in UV and the magnetic field, we can make what we call extrapolations of the magnetic field structure to higher into the solar atmosphere. We'll see like how this layer it's called. We are seeing the sun as never before. These also are images of the sun in extreme ultraviolet, except these images were not taken here around the Earth, but we, humanity, we launched a rocket, a spacecraft in 2020, I think, February 2020, if I'm not wrong. It is called Solar Orbiter, and we launched that spacecraft to orbit the sun in an orbit which is very eccentric, but with a particular fact, which is it gets very close to the sun, closer than the Earth. I think the closest approach for this spacecraft is something like 23 solar radii or something about those numbers. But what is important from these images is for the really first time, we are seeing the sun also in UV, in ultraviolet, but very, very near to the sun. And then you see these bright spots over here, really tiny kind of explosions, kind of like fires over here. Well, we are speculating that those are signatures of small solar flares happening on the sun. Some people like to call them campfires. And if you want to see how big are those campfires, well, this is an image showing at scale the size of the Earth compared to one of those campfires. So even they are tiny for the solar scales, they are still huge compared to the size of Earth. Like, look, like if you put one of these, it's kind of burning the whole, I don't know, the Sahara desert over here. This is an animation of how that spacecraft looks like. It has more than 10 instruments on board. Some of them, yes, as we said, looking at the sun in UV, others looking at the sun in the magnetic field and several ways in situ and remotely, Doppler and intensity and X-rays. It was launching this rocket, the Atlas V rocket.
And international collaboration to give us new images and a better understanding of night-giving stars.
And since then, it's been giving us a new look at the sun. This image, for example, it's near the South Pole. So you can see this is kind of the boundary of the sun, of the bottom. Yes, there is not up and down in space, but kind of in our coordinates, we have a North Pole, if you want, and a South Pole. And this is looking there. One particularly fact of this spacecraft is that it is intended to go outside the plane that the Earth is containing when orbiting the sun around, but that plane we call the ecliptic, and this spacecraft is intended to go a little out the ecliptic. So it is, I think the maximum inclination is about 20 something degrees. So it's gonna give us for the first time images of the solar poles or near polar regions on the sun, which is gonna hopefully bring new physics and at least new understanding of the solar processes. This is the launch. So yes, it was February 2020. And since then, it's been it has had some what we call gravity assistance from Venus again on August 2021, and September 2022, just last year, it got another assistant. and then only until 2025 is going to get the next one. But the orbit, which is the wide orbit over here of that spacecraft, is already very eccentric. It is getting closer to the sun, and it's again providing images as never before. This is one infographics that I like a lot. A few of the instruments in the spacecraft are what we call in situ instruments. In situ means going there and measure. There are two ways of measuring things. So one is with telescopes, and basically that we call it remote sensing, because you remotely are sensing your objects. That is basically what all astrophysics is based on, because yes, astrophysics, the objects are so far away. But for us, for the sun, we have the luxury that we can do both remote sensing with telescopes. Basically, we heritage, to don't say steal, the techniques from night astrophysics and implement and adapt and optimize those for solar observations. But we also measure in situ. So if you see this, the sun is in the center of this image, and then you see the Earth should be like I think the Earth is this one, if I'm not wrong. Yes, the Earth is this one, 1 AU, 1 astronomical unit. And then what is cool is that as the spacecraft solar orbiter moves around the sun, it measures particles. And then what is this infographic is showing is sometimes, most of the times it's calm. There is nothing like big happening, but then suddenly you see like a ton of very energetic particles, and then quiet again, and again, very energetic particles over here. So in some sense, the interplanetary space, meaning the space in between planets, is not that empty. We knew that, but when there are solar explosions, or yes, like these particles, these very energetic particles, should come from somewhere, and indeed they come from the sun. So when there are explosions, the sun ejects large amounts of energetic particles, and we can now measure them very close to the sun. That solar orbiter spacecraft is not the only one that we have to look at the sun. As I said a minute ago, we also use as a heritage or steal techniques from night astronomy. So we can use large telescopes to point to the sun. The largest is your telescope, the better spatial resolution you get. And this is an image of the sun, like the whole sun is over here, this sphere down here. But if you zoom in and zoom in again, you can now see a lot of detail. You see like this granular structure, kind of bubbles when you are boiling water. Those are in fact features of similar physics of boiling water that we have on the sun. And the cool fact is, now by using this what we call the DICES, the Daniel Inouye Solar Telescope, which is placed in Hawaii, we can now see a structure on the solar surface as tiny as the size of New York. So we now have that amount of resolution, and you can like compare one of the cells in here that we can see now. They are as large as one state in the United States. This is very romantic, although it's not Photoshop. It is one of the first images that the DICES observed. Is a heart-shaped sunspot, and observe again with DICES. And something cool about this image is that you see all this bright structure around, and in the center you see all this is very dark. It is dark because there is a strong magnetic field coming out the solar interior at that region, and that strong magnetic field inhibit the motion of the plasma, and motion, kind of higher motion means higher temperatures, and higher temperatures mean more bright. So if the plasma cannot move that easy, it means that this plasma is cooler than the plasma outside in these regions. But something that it's kind of cool, and now it's using in St. Valentine's Day every year, is this image of the sun, of a sunspot, because it has that hair-like shape. This is the Dickes, the telescope that I told you is in Hawaii.
I'm sorry.
Okay, and this is a 4-meter diameter main mirror. So if you compare to the very large telescope in Chile, for example, it is the same diameter as one of the 4 main telescopes that they have down there. So we are mimicking what our night astronomer fellows use, but we are pointing the same to the sun. Some of you may wonder like how to point a large telescope to the sun, and yes, it's not easy. It's very challenging, and you need to filter the light, etc., etc. You never ever put your eye on an eyepiece. That happens also for night astronomy. Once you get like these very large telescopes, you don't see with your naked eye. You use instead optical benches, and the final results, they are projected on the screen of your computer. Okay. I was lucky that last year I could go to Hawaii and visit that telescope, the Dickes, and this is the view. Hawaii has the second or the third best sky on the whole planet to observe astros in general, and the sun is not an exception. And this is also a photo that I could take at that time. And at that moment, the telescope was not doing observations, so it was in its resting position, which is basically horizontal. And here you see the mirror is over here, and the mirror it's vertical. But once it starts making observations, it points to the sun, so it gets horizontal. And something cool to see from this picture is look at the size of this engineer over there, and compare his size with the size of the main mirror of the telescope. So it's a massive telescope to observe the sun. So we are seeing the sun as we have never seen it before. We are living a golden age to do solar physics and solar sciences, because we have new instruments, new technology that allow us to study the sun as humanity had been doing it before. This is another image of the sun that I like, and you notice that this is a solar eclipse. So during a solar eclipse, that, by the way, parenthesis here, there are 2 solar eclipses that are going to cross the entire US in the near future. So one, it's an annular solar eclipse. So you won't see for the annular, you won't see totality like in this picture. It's still it's going to be cool to observe, to watch if you have eclipse glasses. So get your eclipse glasses, or make a pinhole and project that onto something. But that annular eclipse is coming on, I think it's October 14th this year. And there is also the total solar eclipse on, I think it's April the 8th next year. You can Google the dates because I don't remember exactly the dates, but those are approximately dates for that. Anyway, closing the parentheses and coming back here, this is one image during totality. This is a real photo. It wasn't take. It was just obtained on Google. But you see here the moon. It's in the. It's in our in it. It is in between us and the sun. So the moon covers the whole. The lower layers of the solar atmosphere. The sun doesn't finish at the surface that we can see with our eyes. And this is what I want to bring from here, from this image, is once you cover the most bright part of the sun, you see all this structure that looks beautiful, looks like a corona. And in fact, because it looks like a corona, it's called the solar corona. And it extends all the way to Pluto and involves the whole solar system. So here you see some bright red spots over here. They are called, I don't remember, something bellies, belly beans, I think. And they are hot structures of the atmosphere in what it is called the chromosphere. We'll get to look at that. But you see, like all these structures, you can see that with your naked eye next year during the total solar eclipse. And this is also a real photo, and this is among all the photos of total solar eclipses. This is by far my favorite, because you see how the solar atmosphere doesn't finish; it extends and covers the whole solar system. And solar system. I'm gonna say just that. So we have a ton of data from the sun. There is this mission Soho that I think is now 26 year. I need to update this slide, or it's more than that actually. And this is an image, an infographic also showing the sun in UV all the way since the first data in 1996. And then you see all of the way up to 2020. And you see how the sun doesn't look alike all the way from the really first date until now. But there are some dates, like, yes, the really first image, or the one in 2020, in which the sun looks very quiet, very calm, like it's very homogeneous. It's like no many features over here. But there are other times, like around 2000, 2001, and here in 2014, 2015, in which the sun looks way more active. It has more features. It looks like it is about to explode. It looks like it is about to do something. And in fact, you see that this shows a periodicity, kind of like 10 years periodicity. In fact, it's not a 10 years periodicity, it's an 11 years periodicity if you count the amount of features on the sun, and that's called the solar cycle. If you plot, if you make a plot here on the horizontal axis is the date. So you see it starts in this image 2010 and finishes in 2020. And here on the vertical axis, you plot the heliospheric latitude. Then you see that by the end of a solar cycle, you have these two features that look pretty much like a butterfly. And in fact, because it looks like a butterfly, it is called the butterfly diagram. And it is I pretty much love this diagram, and I know many other solar scientists do, because this is a natural outcome of plotting this. We are not tricking the data in any way. And it is the intersection of of science and art. It is like it's very artistic to see these patterns that looks like butterfly coming out of the sun. And that's one solar cycle. But if you go back in time, as long as we have astronomical records of the location of the sun, you see that we have counted a few full butterflies over here. So you see all these butterflies going down to like the 1880 over here. And if you count the amount of features on the sun and you make a histogram, you see that again every 11 years you get a maximum of solar features. I'm calling them features for now, but they are sunspots, they are flares, they are all kind of active phenomena on the sun. And then in between two maximums you see a minimum here in which there are almost no features, and features relate with the activity of the sun. In reality, what happens is the solar cycle is not an 11-year cycle, it's a 22-year cycle if you account for the magnetic field. So you see other two butterfly diagrams over here, one on the top showing this is the emission in X-rays. Also, like horizontal axis is always time, vertical axis is always heliospheric latitude, is the latitude on the sun. And yes, if you just plot the X-ray flux over here, you see this butterfly patterns emerging again. If you see on the bottom, you see that every 11 years, if you divide the plot in these three regions over here, you see that this region is predominantly black in here. This one is predominantly white and black again. So there is a cycle also in black and white. And in this diagram, black and white represent the polarity of the magnetic field. So if from here to here there are 11 years, you see that to complete a full solar cycle, you need something like 22 years. So the real cycle of the sun is more like 22 years. And that happens because of the magnetic field, the global magnetic field of the sun. The global magnetic field of the sun is something like a dynamo, very close to a dynamo. And what a dynamo is if you guys have played with magnets, the most simple magnet is just a tube in which one end has one polarity and the other end has another polarity. And if you draw what we call the magnetic field lines, they make envelopes kind of like ear-like shape. The thing is, we believe now that the global magnetic field has that shape, and that the magnetic field of the sun is produced in not all the way to the core of the sun, but it is produced in at 70% of the solar radii in the solar interior. And one of the, well, I don't want to call it problems, but let's call it problem for a second, is that the starting from that layer above, the sun doesn't rotate as a solid body, but in terms, it is a fluid, and it rotates at a higher speed close to the belly than close to the poles. So the net effect of that what we call differential rotation is that after some rotations, the magnetic field lines start to get entangled, and with that entanglement, you see that some not dipolar but higher structure, more complex structure magnetic fields start to emerge on the solar atmosphere. So you see at the end of the animation over here, you see that some of these magnetic field lines start to show up on the solar surface. Let me just go very quickly to the solar interior. We haven't gone into the interior of the sun, but the models showed us that the sun in its interior is divided in 3 large parts. One at the very core that we call the solar core, and is where the 99% of the whole solar energy is released via thermonuclear processes. Then that energy needs to be transmitted. And in this region, that goes from 20% to 70% of the solar interior that we call the radiative sun. And radiative because the energy is transported via radiation. And then it comes at this continuity layer, 70% of the solar radius, which we call the tachocline, where we believe the solar magnetic field is hosted. It was produced and now is hosted there. And then from that layer up, the energy is transported via convection, so we call that layer the convective sun. How do we know this if we cannot go into the solar interior? Well, we steal a lot of techniques from other sciences, and we stole one technique from earth science, which is seismic. So we haven't dig. I think the deeper hole on planet Earth is something like 10 kilometers or so. We haven't gone deeper into the Earth, into our own planet. And just to give you an idea, our Earth has a radius of 6,400 kilometers. So people here on planet Earth, what they do is to study oscillations on the planet surface, and then kind of get an idea of the planet interior. Well, for the sun, we do the same. Is imagine this is the sun, and it's like a bunch of speakers on the surface. So we study how those speakers oscillate, and we correlate those speakers in a very similar way to what the surface waves of a battery when you hit one of those plates does. So by analyzing the different shapes and motions and dynamics of the solar surface waves, we can get an estimate and an idea on how the sun is in its interior. The sun doesn't finish at what we call the solar surface or photosphere, but we saw that the corona extends all the way into the interplanetary space. But this is more or less how the sun is divided. The sun is divided. So we have a core. This is backwards, I think. Because it is the radiative sun, then the convective sun, then the photosphere, the chromosphere, and the corona. In the corona is very weird. Why? Because the models showed us that if you go with a thermometer to the solar interior and you measure the temperature in the very core of the sun, your temperature is the highest. It reaches 15 million degrees. If you move away from the core, your temperature starts decreasing more, and reaches its minimum at what we call the photosphere, the solar surface. It passes from 15 million degrees to something around 6,000. But then it is like a campfire. If you get away from the campfire, you expect that the temperature decreases and keeps decreasing. So if you move away, you would expect that the temperature decreases, but it doesn't. It increases again, and not by a tiny factor, but by a lot. it increases, it passes from 6,000 degrees over here to values of 10 million degrees. And nobody understands in detail why. Why this is a problem? This is a huge problem because we in solar physics, we don't like to break the law, and particularly what Homer is about to say here, we don't like to break that law.
I know. And this perpetual motion machine she made today is a joke. It just keeps going faster and faster. Lisa, get in here. In this house, we obey the laws of thermodynamics.
So in the Simpsons house, they obey the laws of thermodynamics. And in solar physics, we also want to obey this laws of thermodynamics. The problem is that if you move from a region which is cooler, here, this is showing the temperature from the solar interior to outside into the corona, and if you move away, when you move him away from the source, you get hotter. That kind of goes against the second law of thermodynamics, and we don't want to break that. So in fact, if you go and Google the list of unsolved problems in physics, and if you go into the astronomy and astrophysics section, you see that the corona heating problem is an open question in which many people were still working on. There are some possible explanations now, although it hasn't been fully explained, why the sun's corona is that hot. Some of them, of the possible hypothesis, is that the whole solar surface is full with very tiny solar explosions, and if they exist, they should emit X-rays. Now, and I want to show a little bit of what we do here, and what my work is about is we use an imager that is called the FOXY, it's a cool name, the Focusing Optics X-ray Solar Imager, which is a telescope that observes the sun in hard X-rays using direct focusing. The idea is to try to observe those X-rays for both, one, understand better the physics at large solar flares, but also try to detect those very tiny and faint emissions of X-rays. Focusing in X-rays is challenging. If we use visible light and we use a mirror, then we can get that photon reflected very easily. But if you try to do the same with hard X-rays, well, that hard X-ray, instead of getting reflected, it goes through the mirror. It doesn't mean that you cannot use mirrors. You can use mirrors to reflect rays, but you need two things. One, you need very polished mirrors, and two, you need to use very small incidence angles, and then you can get your ray reflected. So if you can do that with one ray, let's put two mirrors together and then focus one X-ray on two mirrors. And then if you put two more mirrors and focus a second X-ray, so you don't have only one, but now you have two X-rays coming through a single point. And why to use only 4 mirrors when you can use a bunch of those mirrors and focus a bunch of X-rays down here on the focal plane? Well, if you assume that X-rays coming from the sun are these blue photons over here, this is the exact technology that we use in FOXY, in the instrument we work here in Berkeley. And we put one of these optics in here. We focus all the X-rays down onto a detector. And we don't use just one optics and one detector. We use 7 of them. And this is the whole instrument that we put inside sounding rocket, a NASA sounding rocket, and we have launched that rocket already 3 times fully successfully from the White Sands Missile Range here in New Mexico. And we are scheduled to fly again next year in April to do the first ever large solar flare observation in X-ray using direct focusing. We are going to observe at the same time as this spacecraft, which is the Parker Solar Probe. Parker is also another spacecraft as similar as Solar Orbiter, which is very close to the sun. This is Stuart Bale, the PI, and my former thesis supervisor. And this is one of the instruments that are a replica of what is now orbiting the sun in space. This is the launch of that rocket and that spacecraft that was on September 2018. I remember well. And this is Eugene Parker, probably the most famous solar physicist so far in history. And that spacecraft was named after him. He was the first one to propose the existence of the solar wind, which is a wind of high energy particles into the solar corona. And this is a bit of Parker trajectory. In here you see like how it approaches the sun, and then it gets away. Let me just skip this because I'm reaching already the time of the talk. Foxy is gonna fly from Alaska next year to get at the same time, slightly at the same time, with another sounding rocket, NASA sounding rocket called HI-C. And the idea is both of them observing the sun at the same time. What we intend to do is to, with Foxy and HI-C, to observe what happens remotely on the lower layers of the solar atmosphere, while the Parker Solar Probe measuring C2 at higher layers of the solar atmosphere. This is a little bit of one GoPro camera that we put in Foxy. This is the sounding rocket that we flew in Foxy 3 the third time, and this is pretty much what we intend to fly next year in April. And that launch looks like this, except like with the GoPro cameras. You can see how we launched and we point to the sun when we reach space, and we stay. Well, you see some pieces of hardware flying around. That's the nose cone of the rocket coming back to Earth, and we stayed there for a few minutes, and it landed. So this is also to say we study the sun because we want to understand the physics of stars, and this is the closest star, but also because the sun affects Earth in many ways. One, yes, we mentioned it is the source of life, but also because the sun has these large explosions, eruptions, solar flares, and those can hit Earth. Well, we want to see how those explosions hitting air can affect us. So and when the sun ejects plasma, we call that a CME, a coronal mass ejection, and it looks pretty much like that. So the sun here looks green, and then a coronal mass ejection is all this hot material, energetic material going away from the sun. And those ejections of mass can impact several of the planets in our solar system, including Earth. So what happens if one of these emissions hit Earth? Well, to start, they create these beautiful fluorescence rivers and sky that we call auroras. So we have auroras borealis and australis that look like that. The same, but from space. This is an image taken, footage taken from the International Space Station. So you see how cool it looks. And we can even see these kind of auroras in other planets. So this is how it looks on Jupiter, for example. But when a solar storm impacts Earth, not only creates auroras, but these days something that concerns us is that we have many spacecrafts orbiting Earth. And one of these solar eruptions can basically damage the some of these satellites. This is a map showing problems on satellites, and you see on the bottom is the map of the whole planet, except like you see most of the breaks on satellites occur here in South America. Why? Because in South America, with core in Uruguay, we get what we call the South Atlantic magnetic anomaly. And that's a spot on our magnetosphere, and in magnetosphere, the magnetic field of Earth, which is weakest. And because it's the weakest point or the weakest region, the magnetic field of the Earth magnetic field protects the satellite the least, so they are more vulnerable to that solar radiation. We are approaching solar maximum, so that's a little bit of a concern. We are more and more a civilization that depends technologically on satellites. So the impact of these kind of explosions are becoming more and more important for us, for society. Fortunately, we also, as I said at the beginning, we are living in a golden age for solar exploration. We have a large suite of high technology ways to observe the sun. We mentioned the Solar Dynamic Observatory, the Solar Orbiter, the Parker Solar Probe, the two NASA sounding rockets that we are going to launch next year. And this is a CubeSat called Padre that we also are working here in the lab. And we have the Thickest, which is the largest telescope from the ground to observe the sun. So we have plenty of data, plenty of instruments to work with. I'm just gonna finish saying we need hands, we need brains, we need your help. Please come join us. There is a lot of fun, a lot of good physics and good technology, and hopefully we get close to solve the open questions on this field. So I'm gonna finish with that. Thank you so much for being here. I don't know if we have some questions, some time for questions. If not, you can reach me at any social media. I'm as Astronom Milo in every social media, or just come to our website. Thank you so much for your time.
Milo, thank you so much for that talk. If anyone does have a question, we can probably hold on for just a few more minutes. We did have a late start this morning. You can just put them in the Q&A chat. But Milo, I guess I had a question. So you ended on, you guys need people to be involved. And so what would be the best pathway for someone to get involved?
It depends on where in their professional lives are. So examples from I'm going to start from the really top down. From the really top down, professors, researchers, there are more and more projects here and in other institutions. Solar physics interestedly has enough open spots for researchers. So just join in any institution. If you go down into the professional life, if you are a student, just well, if you are a grad student, look into your university and see like who work on these topics. If you are in college or an undergrad and you are planning to go into grad school, there is a list of universities in the US. I think, yeah, it only includes the US. If you go to the Solar Physics Division of the American Astronomical Society, there is a list of universities that have people working on solar physics. So try to apply to those institutions. If you are earlier in your career, join us in public talks like this one. Join REU programs. Right now, for example, here we are running one. I know in Boulder, they are also running one. At the Smithsonian, they are also running one, and in several institutions here in the US. Contact people, email people. When I was younger, when I was an undergrad, someone told me just email them. I was very afraid. It's like I'm nobody, and I was feeling that. Just overcome that, like send that email. Worst case scenario, they respond, and I'm saying worst because then you are gonna get busy if they respond. And usually, like a good percentage of the times, people respond. So just send those emails, start contacting people.
Yeah, so get yourself out there.
Yeah.
When looking at your most recent project, your focus is on astrophysics, but you must be working with a team of various engineers and things like that. So it's not just astrophysics. So what is your working relationship maybe as someone that has to work with IT and various engineers on a large project like this?
Yeah, something that I love the most out of these projects is the diversity on different backgrounds and different professions. We get to work with a lot of engineers, and I love working with them. I'm one of the scientists in the team, but I can tell you, like, I work with electrical engineers, mechanical. I love working with mechanical engineers. They always make fun of us scientists, saying like, never leave your experiment alone with a scientist because they are gonna break it. And yes, so they help us. We it's not that they help us. We collaborate together a lot. It is a very diverse team. So if you like one of those engineering fields, say mechanical, electrical, computer science, going to them, knowing that it is possible to get involved in space sciences and work shoulder with shoulder next to a team of scientists to basically try to solve open questions on space physics and astrophysics. They love this field. I can tell. And although like in industry kind of like all the time try to pull them away from space sciences, it is such a fun job that they don't leave. They basically stay at the lab working with us until they retire. This is a really passionate, fascinating field to be in.
That's great. So there was one question, and that was actually asking, what is your Instagram ID? Was that on your last slide?
Yes, it is Astronomilo. Let me share that again. Yeah, in Instagram and in all social media, I'm Astronomilo. Like,
okay,
I'm gonna leave it there.
I have one last question. So
yes.
you had a great job. Actually, someone else has a question. I'll take theirs instead of mine. So what does your day-to-day life look like? How much time is spent coding, etc., and what does a scientist really do?
Yeah, it varies, and that's probably one of the most cool things of this job is you don't have a repeated day. Every day is different, and you have seasons. Like right now, we are preparing to deliver our rocket payload. So it is very, very heavy on the instrument side. So right now, after this talk, I'm gonna close my laptop and run to the lab and get some benches moved from one lab to the other, because today we have visitors from the University of Minnesota and Japan who are coming here to the lab to work together and start like putting together the different instrument parts of the whole telescope. So it is pretty much a screwdriver on one hand, multimeter on the other hand, run from one lab to the other, move stuff, measure here, turn lasers on and off, things like that. But this is a season, like this is gonna be, and I know it's gonna be like that the next couple of months. Then we get the rocket launch. So before the launch, it's going to be probably a lot of coding, because one of the big challenges that we have is going to be the first rocket to observe this solar flare. And we don't have the capability to predict when a solar flare is going to happen with 100% certainty. So we need to come up, we have some strategies already and we test some things, but we are in early stages still. So we need to work more on coding and come up with a good strategy to get a trigger for the rocket launch, and knowing that, okay, a solar flare is happening, press that button and launch the rocket. And one thing with this kind of projects is that you get to launch the rocket once, and once it's out of ground, it is gone, and it's gone, and it is not going to come back. You don't have second chances, so you need to be sure about that. So it's going to be a lot of coding. And after the launch, it's also going to be a lot of coding, but in a different way, because before it's kind of like, okay, we need to solve this application, and it's a direct application. After is, okay, we got this very exciting, unique set of data, and let's analyze that, and let's understand how the instrument response was, and extract the science, squeeze the data, and get the science out of the data that we obtain. Hopefully, like fingers crossed, we get good data. So it is very different. It varies. There are years in which you pretty much travel a lot. That's one thing that nobody told me when I was an undergrad, and I would have loved someone told me this, which is you get to go to a lot of conferences in very exotic places around the earth. I told you, like I showed you an image. I never hopped to go to Hawaii, and last year I just got to go there. Why? To present my results, and at the same time you get to explore a little bit. So that kind of periods happen, and it is not boring at all. It's very different all the time.
You forgot one part. There's a lot of writing too, isn't there? When
Yes.
you want to publish articles and for your dissertation.
Yes.
So there is
Yes.
writing in the life of a scientist.
That's very true.
No, but it is dynamic, which is I think a fun part of it.
Yeah.
Okay, so one more question. What are the major challenges for humans to discover any new ways for space travel and space research? Challenges for humans.
Yeah. Challenge for human. I'm gonna say, well, I'm gonna divide that in two sections. So challenge for humans, I'm thinking like it's the same challenge that humans face in any other field, which is collaborating. Science is still like in its way up to learn more and more how to collaborate more and more with a diverse group of people. That's happening, but that's slow, I think. And all the different challenges that come with social and human-to-human interaction. And there is the other challenge, which is about science itself. So it's about finding new physics that we can use to improve our technologies. and implement that into space exploration. So being more concrete, for example, making solar sails. That's one thing that is coming, but it's challenging a bit. We somehow have already some technology, so we could do that. But then we need to prove there is, so far it hasn't been done, like unfold a large solar sail into space, large enough to push a small payload away from our solar system. But that's one way to do it, and probably it's gonna come in the next years or a couple of decades, I'm gonna say. There is also like finding new, very exotic new ways of traveling, space traveling. So the Alcubierre, how that's called, a space time way of traveling. So basically, kind of like being able to stretch and handle space time in some exotic ways to kind of like go very far into the universe. That could happen, but so far we don't have that technology. There are some ideas, but until they are tested in nature and corroborated observationally, they are ideas. They are really cool ideas that we need to keep exploring. So, and I'm gonna end saying all of this can happen with the new way of doing science, which is not a single Albert Einstein or a single Dirac. Today, big science is made by big diverse groups. So we need several people from all kind of backgrounds and professions working all together with same target.
Yeah, I agree with that. Well, thank you so much, Milo. This was an excellent talk. And so on behalf of the REYES team, we thank you for sharing your knowledge, and those of you that joined us today. Please check the REYES calendar for any of our next events this week. And again, thank you, Milo. What an excellent time we had with you today.
Thank you, Rachel, and thank you all.
Thank you. So Clay or Jeff, I think we can cut off the YouTube live now.